Friday, you guys were doing a lab where you burned some food samples and captured the thermal energy and measured how much energy was actually coming from the food. And I want to review some of that with you, make sure we understand what's going on and really how a calorimeter works. Okay, so let's run through some of the pre-lab questions and then we'll get into some of the calculations and see what happened. Okay, so the first thing it asks us is, what kind of energy is stored in food? I mean, after all, we eat the stuff to get energy out of it. And really, it's called chemical potential energy. Now remember, something has potential energy because of a force that acts on it. Gravitational potential energy is caused because there is a force of attraction between two objects with mass. Elastic potential energy is caused because of the forces in the spring or the rubber band or whatever's trying to pull or push on the object. Chemical potential energy is energy that is stored in chemical bonds. Okay? And basically the main thing that we use for energy that our cells break down is glucose, C6H12O6. And all the food we eat goes through cellular processes, and we take this thing and we break it down into carbon dioxide and water. And of course, to do that, we also have to breathe in some O2. Okay? So chemical potential energy in our food, stored in this big molecule right here, is released because you can see this big molecule is going to be broken down into a whole bunch of smaller molecules. We're going to get 6 carbons out of this, 6 waters out of this. Okay? And so there's more bonds, so it's more stable, and so some of that energy was released, and our body uses that energy. Okay, to live and breathe and eat and whatever. All right. If a sample is burned, a sample of food, what happens to the energy that was stored in the food? Well, it's converted. Okay, it's converted to thermal energy, and we can measure that. In fact, this is actually how they measure the energy content of food. They don't use a pop can and a wood splint. They use much more sophisticated equipment, but it's the same process. In an oxygen-rich environment, they light the food sample on fire, they burn it, they see how much thermal energy is released, and that's the energy content of the food. Okay, so you guys had to go ahead and collect some data for this. Now, it didn't really matter if you got the graph so much, but it was important that you got the temperature change, because the way we calculate heat, or energy gained, is Q equals MC delta T. So you were able to take the temperature change of your sample of food, the mass of the temperature change, sorry, of the water in the can, and figure out how much heat they absorb. Okay, so that's what the rest of this data table is kind of all about. It's going through and getting what you got. So I can't remember what you guys burned. You might have had a marshmallow and a nut of some kind. Not really sure. It doesn't really matter. Okay, the initial mass of the food and holder and the final mass of the food and holder. The reason we need this is because we're interested in how much food burns. Sometimes the entire thing burns, sometimes just part of it burns, but we do need to know how much of the sample burned. The mass of the food burned, this is the difference between these two things. So difference of these two. Okay, and it's going to be small. I'm guessing less than 3 grams. Might even be less than 1. Depends on what you burned. Mass of can and water. Mass of empty can, mass of water heated, right? So you got the mass of the empty can, you added some water to it, and you got all of that. So the mass of the water heated is whatever the difference between these two is. Okay. Final temperature and initial temperature, you had to record those. I don't know what they were. Your temperature change is, of course, the difference between that. Now, the heat is going to be the Q of the can plus the Q of the water, right? And so you had to go through and do 2 different calculations here. Find the change in temperature of the water, change in temperature of the can for each sample. Okay, and we did that up in the table above. Now calculate the heat absorbed by the water. So you did Q equals mass of the water, and it should have been somewhere between 50 and 100 grams, M times the specific heat of the water, 4180, times the change in temperature, whatever you got from the table, and you got a value for that. Okay, that's the energy absorbed by the water. You do the same process for the energy absorbed by the can. The can is aluminum. This is the specific heat of aluminum, so that tells us that. These two energies together, as it says in C, gives us the total energy content of the food sample. Okay, so C is the sum of these numbers represents the energy released. So you add these two up and you get how much joules of energy came out of it. Now, this says kilojoules. It could have been joules. Doesn't really matter. I think it actually, we will use joules. I don't know why it says kilojoules, but these numbers are the energy that came from the food. At least it's the energy that we captured that came from the food. It says, so find the mass in grams of the food sample burned. Again, that's the difference between the starting and ending food sample and holder. And use the results of step 3 and step 4 to calculate the energy content in joules per gram of each food sample. So we take this sum, okay, so total Q divided by the mass of the burned food. Okay, not the total mass, but the difference in the two. And that tells us the energy content in joules per gram of the food. Okay. Now this information is actually also reported on the nutritional label. When you read the nutritional information on a food item, I guess, it's actually telling you how much energy is stored in a serving size, and usually it gives the serving size in both volume and mass. Okay, so which food had the highest energy content and which had the lowest energy content? They were actually fairly close to each other according to their nutritional labels. I'll tell you what those are in just a second. But I'm guessing that the nut probably produced the most energy. I'm not sure. Okay, some of them were fairly close, so it might have been the nut or it might have been the puff corn if you guys burned puff corn. Okay, so food energy is often expressed in a unit called calorie. There are 4,180 joules in 1 calorie. Now that's calorie with a capital C. Okay, calorie with a lowercase c is 4.18 joules. So a capital C calorie is actually a kilocalorie. Based on the class average for peanuts, calculate the number of calories in a 50-gram package of peanuts. Okay, you guys just burned it once, so you don't really have to do that calculation. All right. Some of the foods in this experiment have a high fat content. Nuts have a high fat content, while the others have a high carbohydrate content, marshmallow and puff corn. Although if you burned puff corn, you saw some oil dripping out of it. There's actually quite a bit of fat in puff corn too. From our results, what generalization can we make about the relative energy content of fats and carbohydrates? Now this should be something that you guys are familiar with. Okay, carbohydrates are things that have carbon, hydrogen, and oxygen in them. And they're fairly simple, okay? And your body can break them down in a hurry and you get energy out of them in a hurry. But they're inefficient methods of actually storing energy compared to fats. Fats have big, long carbon chains. They don't have the oxygen atoms in there, and they're holding more energy in the bonds because there's more oxygen that can form bonds with them, okay? So generally speaking, fats are going to be more energy rich than carbohydrates, and that's why your body stores excess energy as fats. Okay, fat is a buildup of energy. You eat too much food, your body stores that energy as fat, and it's a very, very efficient way of storing it. It's also a little bit harder to burn. I don't know if you guys noticed that, but it was harder to light a nut on fire than it was to light a piece of popcorn on fire or a marshmallow on fire. Okay, carbohydrates are quick and easy burn. They're a quick, easy source of energy. Fats are a little bit harder to get burned, but once they get started, once you actually switch into burning fats, there's a lot of energy in them. All right, look up the nutrition information on the foods you burned. How do your results compare to the energy values on the package? Okay, nuts have an average of 180 calories for every 30 grams. Okay, so you can use that value, 180 calories per 30 grams. The puff corn is 160 calories. 160 calories per 30 grams. So that's the puff corn. Okay, and the marshmallows are 100 calories per 30 grams. 100 calories per 30 grams. And again, I just got this information right off the nutritional information. So use the values that you calculated in the table on the other page to compare, right? Did you get 100 calories per gram? Now how are you going to get joules to calories? They give you that conversion up here, right? So it says there are 4,180 joules in 1 calorie. So whatever energy content you have, you got to divide by 4,180 to figure out how many calories you had. Okay? All right. Identify major sources of air that can account for these differences. Now, you guys probably already have this, but you had this setup where you have a can suspended over a fire, okay, and there's water in here, and you got a thermometer in the top. Okay. Where are your major sources of air coming from? They're coming from this fire. Okay. What's being heated? Yeah, sure, the can's being heated. Sure, the water's being heated. So's the air. Okay, a lot of this heat's escaping out the top. Okay, maybe some of the water actually boiled away. You don't have a good controlled environment here. So the major sources of air is heat loss, right? The whole process of calorimetry depends on the assumption that the energy before and the energy after remains constant, right? The whole thing depends on conservation of energy. And energy is always conserved, but you have to make sure that you're accounting for all of it. And if you're not, then you're going to have major sources of air. Okay, generally when we do this lab, we have somewhere between actually 30 and 40% of the energy that they say is present in the food, we actually capture in the can. Okay, so where's all that energy going? All right, well, heat is actually the flow of or transfer of thermal energy, and so how does thermal energy move around? How does it get from one place to another? Okay. There's three methods. Okay, there's three ways heat transfers, and I think you guys are already fairly familiar with this. Okay, I know we talked about it in Science 9. I'm sure you've talked about it in other classes as well. There's conduction. Okay, conduction happens in solids. If you think about a solid, it's made up of little atoms, tiny little particles that are all in contact with each other, right? They form a crystal lattice. They're all hanging out. Okay, they're all together. They're all touching. Okay, and when something gains temperature, what that means is this little particle starts to vibrate a little bit faster, vibrate a little bit more. Okay, so if I stick this end over here in the fire, okay, these particles start to vibrate more and more. Well, that means it's going to bump into this particle, which then bumps into this particle, which then bumps into this particle. It's like the domino effect, right? And so this heat transfers through the particles without moving the particles from their positions. So yeah, this end is really, really hot, and eventually the heat travels over here and it also gets hot. That's conduction. Happens in solids when particles in contact hit each other, and the kinetic energy starts to transfer. Convection is the second method of heat transfer. It involves matter as well, and it's actually sort of a special case of conduction. Okay, convection happens in fluids. Okay, now a fluid is a solid, or not a solid, sorry, a fluid is everything but a solid. It's a liquid or a gas. Fluids can flow, right? And so in a fluid, we don't have that structured, orderly arrangement. And not only that, there's nothing that says these particles can't move. So if you think of like a pot of water sitting on the stove, okay, there's conduction at the bottom, right? You got this pan around it. You've got fire underneath it. Okay, there's conduction. This thermal energy right here starts heating up this pan right here. It gets hot. It smashes into these particles. These particles actually start to spread out from each other because they're gaining energy. They're moving more. And as that happens, they become less dense, and so they rise up to the top. Okay, they start to float. And so these cooler, denser ones, they start to sink back down here, and so then they get warm and rise to the top, and you get this circular pattern of heat transferring from the heat source throughout the liquid. This is called a convection current, and this is actually heat transfer by particles. Okay, conduction was heat transfer by vibration. This is heat transfer by particle motion, by particle movement. Okay, because these particles are not fixed in position. They actually are moving around, and this is actually a very important type of heat transfer. Convection currents are responsible from everything from rain and snowstorms to tectonic plate drift to tornadoes. So these are the things that drive our weather and our continents across the surface of the Earth. Convection in fluids is kind of a big deal. Okay, but when we had this can sitting here, okay, over fire, Okay, and water here, well, convection, there's air around here, it's going to start taking that heat away. Conduction, yeah, it's going into the can, but it's also going down into the food holder and into this tray down here. And so we're losing heat here, we're losing heat here. So there's those two things, and we can do a lot to reduce that. We can trap some of this energy. We can try to make this more of an isolated system. But there is one type of heat transfer that's really hard to stop. Okay, and the last type of heat transfer is called radiation. Radiation is heat transfer by electromagnetic waves. Okay, light is an example of an electromagnetic wave. Infrared, if you've heard of that, electromagnetic wave. Ultraviolet, electromagnetic waves. So radiation is heat transfer by electromagnetic waves, and this is the one that requires no matter. Okay, requires no matter at all. Conduction and convection both rely on particles colliding with each other. This requires just a field. Like a gravitational field can exert a force on a mass, an electromagnetic field exerts a force on a charge or a magnetic particle. Now, electromagnetic waves propagate themselves, but okay, we'll get into that maybe later. Anyways, these things are responsible for transferring heat from the sun, which is what, 98 million miles from Earth to Earth, through a vacuum. Okay, that's kind of impressive. The sun's 98 million miles away. You go outside, you can feel it. Okay, and you can feel it because electromagnetic waves transfer its energy across the vacuum emptiness of space to us. And this one is really hard to stop. Okay, it's hard to stop radiation. It's hard to block it. All things radiate energy. The only thing that wouldn't radiate energy is something that would be at like absolute zero. There's no such thing. Okay. All right. Now, how do we get better results then? How do we improve this? Well, the answer is insulation. Okay. Insulation means we're preventing heat transfer. So insulators are just poor conductors, and really the best insulator is a vacuum, because there's no matter, nothing can transfer through it except by radiation. And radiation, yeah, for the sun, which is huge, is a pretty powerful thing, but radiation is a pretty slow method of heat transfer as far as, you know, if you've got a thermos of hot coffee and you want to keep it hot, a thermos is actually a vacuum bottle. What it is there's an outer chamber, okay, and then an inner chamber. And a high quality thermos, this chamber, this space in between, there's nothing in it. It's a high vacuum. They've pulled out as much air as they can, and that way there can't be conduction because there's no particles in between. There can't be convection because there's no fluid in there to transfer. And so basically your heat loss is limited to radiation, and right here where the two stick together, there's a little bit of conduction. Okay, so every time you open the lid is when basically most of the heat gets out. Okay, insulation, most insulation is actually working in two ways. First, it traps air, and second, it prevents that air from moving. Okay, like fiberglass insulation is fluffy, and the reason it's fluffy is because we're trying to make little air pockets, because air is actually a very good insulator unless it can move, because if it can move, it can set up a convection current. And so, right, if the air was free to flow and I had a temperature difference on two sides of a wall, say, like the inside of your house is warm and the outside of your house is cool, if the air in your wall can move, then the warmth is going to spread into the more dense, right? This is dense, and this is going to be less dense. So it's basically it's a convection current. This less dense stuff tries to escape. It's getting warm, it heats up, it tries to move this way, and that'll give an empty spot for this cooler, denser air to fall into, and you'd set up this convection current, and your heat would be transferring out of your house. Okay? And so to stop that, we fill up this gap with insulation. Now what the insulation does is it creates these little air pockets, and these little air pockets are small enough that the air can't really move very well. Its molecules are trapped. Okay, air is a very poor conductor because the particles are spread out. They're not really touching each other, and as long as it can't form convection currents, then it can't really transfer heat. So the insulation works by trapping heat, by trapping air, and by preventing their motion. Okay, air gaps are bad. Like in double pane windows, there's a maximum space you want between them, because if you get too big, then the air can actually start to set up convection currents. Anyways, we're going to look at actually using an insulated calorimeter to make some better measurements, and we're going to see if it really matters. Does the insulation matter in a calorimeter? How much of a difference does it make? Okay, so we're going to use a real calorimeter to do another lab, and we're going to measure the specific heat of a couple metals. Now, remember, the idea of a calorimeter is that it traps energy, and the energy gained by one thing is exactly identical to the energy lost by another. And so in preparation for this, I want you guys to take a look at a couple problems. I want you to do problems 6 through 9. That's really too hard to read. Problems 6 through 9 on page 321. Okay? And it just does a couple calorimetry problems. And the thing to keep in mind on a calorimeter is the energy lost by one substance is exactly identical to the energy gained by another substance. Okay? Good luck with that. If you have any questions, let me know.